Hello guys, and welcome back to Introduction to Number Theory. In this video we will discuss an interesting mathematical problem, solved problem of course, which turned into a theorem called Sylvester's theorem. First we begin from a situation from life. Well, suppose you're given an unlimited number of banknotes of 3 and 5 rubles. Well, it seems silly nowadays, but actually such banknotes rarely existed. What is the largest amount that cannot be issued using only banknotes of 3 and 5 rubles? Well, for instance, 3 plus 5 is 8, so we can issue 8 rubles, and 3 plus 3 plus 3 is 9, so we can issue 9 rubles, and we can issue 10 rubles, and then we can take 8 rubles and add 3 more to gain 11 rubles, and 9 plus 3 is 12 rubles, and 10 plus 3 is 13, and we understand that any amount of rubles starting from 8 can be issued by banknotes of 3 and 5 rubles. But what about 7, the amount of 7 rubles? Well, 7 cannot be issued using only 3 banknotes of only 3 and 5 rubles. The generalization of this problem is taking arbitrary natural positive integer, mutually prime a and b, and ask ourselves what is the maximal c, the greatest, largest c, also positive integer, such that c cannot be represented as a sum of several a's and several b's. Well, a plus a plus a plus and so on, plus b plus b plus b and so on, is actually just ax plus by, where x and y are non-negative integers. So the question is, what is the maximal, what is the greatest, largest c that cannot be represented as a linear combination of a and b with non-negative coefficients x and y. In other words, we understand that any large enough amount, any c large enough, can be represented in such a way. And Sylvester's theorem claims that the maximal positive integer c, not represented as ax plus by with non-negative x and y, is precisely ab minus a minus b. Let's check this theorem first. Well, take a equal to 3 and b equal to 5. Well, really, 3 multiplied by 5, 15 minus 3, 12 minus 5, 7. Well, indeed, 7 was the greatest, largest amount that could not be issued by banknotes of 3 and 5 rubles. The interesting thing is that James Joseph Sylvester, who proved this theorem, he lived a long time ago, but still we don't have a nice enough formula for a similar problem with 3 numbers, 3 integers, say a, b, and 1 and some more integer c, and what is the smallest integer d, what is the greatest integer d, such that d cannot be represented as ax plus b y plus cz with non-negative x, y, z. Just an analogous problem for 3 variables, not a, b, but a, b, c. Still does not have a formula for the greatest non-represented integer. But now let's prove Sylvester's theorem. So we'll be dealing with mutually prime a and b, positive integers, and the claim actually consists of 2 parts. First, we need to show that ab minus a minus b really cannot be represented as a linear combination with non-negative coefficients. But then we need to prove that any integer greater than ab minus a minus b, any integer greater than this one, can be represented as a non-negative linear combination of a and b. The first part. So we will prove that ab minus a minus b is not equal to ax plus by for any non-negative x and y. Suppose that it is equal to something like ax plus by, and suppose that this x is x0 and this y is y0. So ab minus a minus b, the first line of the proof, we set it equal to ax0 plus by0. Then just transform this equality by taking a and b from the left-hand side to the right-hand side, and take a look at the second line of the proof. Well, there are rather many summands divisible by a, right? ab is divisible by a multiplied by x0 plus 1 is divisible by a. So b multiplied by y0 plus 1 must be divisible by a. But b and a are mutually prime. So y0 plus 1 must be divisible by a. Similarly, x0 plus 1 must be divisible by b. Okay, but we know that x and y are greater than or equal to 0. So when enlarged by 1, they are positive. So a positive number divisible by b, well, it must be at least b. So x0 is at least, which means greater than or equal to b minus 1. And y0 is at least a minus 1. Okay, but if x0 is at least b minus 1 and y0 is at least a minus 1, well then a multiplied by x0 plus b multiplied by y0, the fourth and the last row, the last line of the proof, will be strictly greater than ab minus a minus b, which is a contradiction which proves that, well, indeed, there are no such non-negative x0 and y0. This was the first part of the proof of Sylvester's theorem. Now, the second part. We need to take an arbitrary c greater than or equal to ab minus a minus b plus 1, which means that it's strictly greater than ab minus a minus b, and prove that such non-negative x and y exist. Well, first consider just a linear Diophantine equation with simply integer x and y, integer unknowns. Then we know that solution, since a and b are mutually prime, a solution exists, and it has the form of x0 plus bt and y0 minus at. So by varying this t, we can make y between 0, including 0, and a minus 1, including a minus 1. So choose such t, and now we can use that, from now on, use the fact that y, the solution of this linear Diophantine equation, is between 0 and a minus 1. And then express x. X will be equal to c minus by divided by a. And what is the lower bound of x? Well, c is greater than or equal to ab minus a minus b plus 1. So we use this value instead of c. And y is less than or equal to a minus 1. So we use this value for y. We simply substitute these values instead of c and y, and we obtain that x is greater than or equal to minus 1 plus 1 over a. But since x is an integer and it's strictly greater than minus 1, then it is non-negative. So y is non-negative and x is also non-negative, which finishes the proof of Sylvester's theorem.